I think an example problem may help solidify some of these ideas for you. So let's look at a simple problem with 2 point charges, Q1 and Q2. One's positive and one's negative. And they're fixed to a coordinate system. We're going to move a third charge from point A to point B, and that third charge is plus Q. If you want, you can redo this problem and make that third charge negative and see how your answers change. The first question, what's the potential difference between points A and B? For you to get the most out of this, you should pause the video each time and try it yourself. Then come back and watch me do the solution. For the potential difference between points A and B, potential difference is always final minus initial. If we're going from A to B, the potential at point B is our final position, and at point A is our initial position. And we have 2 point charges that are contributing and causing the potential at point A and point B. The potential at point A is a combination of the potential from charge 1 at point A and the potential from charge 2 at point A. Charge 1 is positive 2Q, and it's a distance of 5. Let's just assume we're in meters here. And charge 2 has a negative 3Q charge, so don't forget the minus sign. And it's also a distance of 5 away. Let's check those distances one more time. The distance 1, 2, 3, 4, 5. The distance between Q2 and point A is 5 units. And the distance between Q1 and A is also 5. That's a 3, 4, 5 right triangle. So we have 2/5 minus 3/5, negative 1/5 KQ for our potential at point A. Let's do the same thing for point B. At point B, the charges are still the same, plus 2 and minus 3, but the distances are different. The distance from 1 is 4 units. Let's call it meters. And the distance from 2 is 2 meters. I get negative KQ for my potential at point B. So if we're trying to find the potential difference, we're going to get minus KQ, and we have to subtract from that a negative 1/5 KQ. So our potential difference is negative. Ask yourself, how does that change if you're moving a negative charge between points A and B? Did you think about it? It doesn't change. The potential difference depends on the field that exists in that region of space. In this case, the field that exists in this region of space between points A and B is due to 2 point charges, Q1 and Q2. Delta V depends on that. It does not depend on the charge that we're moving at all. We can move a positive charge, we can move a negative charge, it doesn't matter. We can move a small charge, we can move a big charge, it doesn't matter. Delta V only depends on the field that exists in this region of space that we're interested in. Now we're asking, what's the work done on our third charge, Q, that we're moving between points A and B, what's the work done on that charge by an external force if this particle starts and ends at rest? If it was at rest at point A and it's at rest at point B, how much work did an external force do on this particle? For work, I always like to think in terms of the absolute value. And I find the absolute value of the work first, and then I decide, does this work have to be positive or negative? It's just easier for me to not have to memorize equations and get them mixed up when I can figure out very easily if it's positive or negative. So this is work done, and typically this would be the work done by the field. But if the particle starts and ends at the same speed, it had no change in kinetic energy. So whatever work the field did moving it from A to B, an external force had to do an equal and opposite amount of work in order to keep its kinetic energy the same. If we release the particle from rest at point A, and the field pushes it and does positive work on it, pushing it to point B, that would cause the particle to move faster and faster and faster. And if we want it to end at the same speed it started at, we would have to reach in with an external force and do negative work on it, slowing it down. Vice versa, if the field would not cause the particle to move from A to B, if we let go of the particle at point A and the field would push it in another direction, we would have to reach in with an external force and push it to point B. And if we want it to start and end at rest or at the same speed, the work done by the external force that we're pushing with would have to be exactly equal and opposite to the work done by the field. The work done is Q delta V. We just found delta V. We said Q was positive Q, but we're just interested in the sign. We're just interested in the magnitude right now. I know that the absolute value of the work done is 4/5 kq squared. Now I have to figure out the sign. Let's go back and look at our situation one more time. The potential at B is smaller than the potential at A. -1 times kq. -1 is a smaller number than -1/5 because we're talking about a scalar here. -1 is smaller than -1/5 is smaller than 0. That's why our delta V is negative, because the potential at A is greater than the potential at B. The electric field always points toward lower potential. So we know our electric field has to have some components, some part of the electric field has to be pointing from A to B. Some part of the electric field has to be pointing from A to B because the electric field points toward lower electric potential. And the potential at A is greater than the... Our Q, little q here, that we're releasing at point A, is positive. Positive charges want to move in the direction of the electric field. They feel a force in the direction of the electric field. So the electric field is pushing on it from A to B. It's moving from A to B, and that means the work done is positive by the field. The work done by the field is positive. Let me write that here. We know the magnitude of the work done. Now we know the work done by the field is positive. If the external force does the exact same amount of work but the opposite sign, then it would be negative. So our answer for this problem, since it was asking for work done by the external force, and our last question, what is the change in electric potential energy of the system when we move this lowercase q from point A to point B? We know a couple of things about electric potential energy and work. We already used the equation on the right to find the work done. Now, we don't want the work done by the external force. We want the work done by the field for this equation. This is the work done by the field. We plug that into our equation, we get delta U is minus 4/5 kq squared. Does that make sense? Should the change in potential energy of the system be negative? Change in potential energy is final minus initial, and it's negative. That means the potential energy that the system had stored in it at the initial condition, when the charge was at A, has to be greater than the potential energy stored in the system at the final position. It's like dropping a pen in a gravitational field. The pen field system has a certain amount of potential energy stored. If you let go of it and the pen starts moving in a certain direction, it goes faster and faster. It gains kinetic energy, so it has to lose potential energy. The potential energy has to go down if the pen is gaining kinetic energy. Well, what happened in this case with our particle? We released it from point A, and the field started pushing it toward point B, and it started to go faster and faster, gaining kinetic energy because the field was doing positive work on our particle as it was moving from A to B. And where did that energy come from? It came from the potential energy that was stored in the system. So the kinetic energy of the particle goes up, and the potential energy of the system comes down. And if you want to go through and do this problem again for a negatively charged particle, that would probably be a good exercise.